This time, we are going to apply the control analysis to demonstrate the sensory feedback involved for the walking. Okay? So at this point, you might think about, wait, walking, we learned intensively about how passive dynamics could well demonstrate human walking in previous chapter, chapter 2. What are you talking about the additional sensory feedback? Well, real human walking, like a 3D motions, are heavily controlled, right? And then here we are going to explain, apply the control scheme in the lateral direction, okay? To do so, I'm going to briefly introduce the active control at the higher center, the brainstem and cerebellum. Those the brain part is responsible for controlling the locomotion, and that needs integrated multiple sensory information from visual, vestibular, and proprioceptors. So here we hypothesize that active control is necessary for lateral stabilization. Okay, so for fore-aft motion, like a sagittal plane motion, we will still use those passive walking scheme, and instead for the lateral motion, we are going to introduce the sensory feedback and how those hypotheses could be examined through the experiment. Okay, once we set the lateral motion requires a sensory feedback, how would you prove this? Well, the previous study, like for the posture control, when you assume the sensory feedback, that means whenever there's a sensory disturbance applied, then the response will show the grade change, right? In that sense, we could examine that by perturbing the sensory information for walking, like eyes closed walking, visual sensory information perturbation. We will see the grade change for the lateral directional gait response compared to the back and forth, so forward and after directional motion. Okay, that's the kind of concept that we could prove that sensory feedback involved for the walking. Other than this, there are another important concept for the locomotion, the rhythmical repeated motion description, like a central pattern generator. This is not about the whole sensory feedback. This is at the spinal cord level reflex control. So this is also interesting topic, but we are not going to cover in this course. So for those who are interested in, I recommend you to refer for the papers. Okay, let's work on then 3D model. So far we've been so familiar with the modeling for the sagittal plane. So sagittal plane, simply two-legged passive walker joint at a pin joint. Okay. For the frontal plane, left and right side, okay, medial lateral side, there are roll displacement. Okay, so those leg abduction. So it's this way, okay, this and this way. And there are torques applied at the pelvic joint, okay? That's the sensory feedback, what we assume in this chapter. So to demonstrate the equations of motion, there are 4 state variables for the sagittal plane, what we have been worked on intensively in the previous chapter. And in passive walking, there's no actuation, no control, okay? For the roll, the frontal plane, there are two state variable, the roll and roll dot, and there is sensory feedback applied at the at the pelvic joint. That's what we assume for the 3D walking model. And of course, those motions interact for sagittal motion state variable to the frontal plane dynamics. However, let's assume that there are weak coupling between them, so the equations of motion could be obtained separately. Okay, so with that, we have total 6 state variables, including the roll states. So that's augmented state variable and its state space form. Okay, x dot equals augmented x dot equals ax plus bu. Okay, how we can set the feedback control? Since we assume the state feedback, the controller, the brain stem, send out the control input to the lateral dynamics, okay? And those lateral dynamics, the rotational motion, are sensed by sensors, and those informations are sent back to the controller again. That's a sensory feedback, okay? For sagittal motion, we still assume the passive scheme passive framework, so passive walking framework. So the stance leg and swing leg, once the initial conditions are set, those are just passive walking in sagittal motion. And the torque applied, and then in between them there are weak coupling. And the torques applied, well, the torques applied at the hip joint, the pelvic point in the roll direction, is going to be augmented state values error. Okay, that's what we assume. So by tuning the gain, we will be able to find the repeated gate cycle. Okay, so by selecting the repeated gate cycle, one of the possible gain set is like this. Since we have only one torque and 6 state variable, there are 6 by 1 gain parameters. As you can see here, there are significantly large gain at the roll state variable for the roll joint torque. Okay, the other variable also contribute for the feedback torque generation, but very, very small value. So relatively light coupling exists between the lateral motion and 4F dynamics. Once you find the fixed point, just regularly you should check the stability by checking the eigenvalues and so on. Very similar manner. So if for the more detail, you can also refer the reference, the suggested reference of Bobby paper. So how we can perform the experimental design, how we can design the experimental protocol to prove the hypothesis. So we should definitely collect the data for the human subjects for the lateral displacement and the fore-after displacement, okay, since this is two-dimensional, like frontal and sagittal. And by one way to apply the sensor noise, we are going to collect the data with eyes open and closed. Eyes closed, sensor noise, larger sensor noise, so your visual sensory information turns out to be 0, right? And we are going to collect, they have collected 15 subjects data for 100 steps. And by implementing those sensory perturbed triers for the model is by adding a sensor noise to the feedback loop. Okay, so the feedback loop is actually for the roll directional state variable, roll and theta roll and theta dot roll. And not only having those pelvic joint torque, we also have a sensory noise on it. Okay, so by having that, you have augmented input term. Anyway, so those sensor noise are going along the loop to the feedback for the lateral foot placement, so that the lateral foot placement will have a significant change by the sensor noise, the eyes closed trier. However, for the feet sagittal plane has sort of missing feedback. It's not feedback loop, so those noise wouldn't greatly affect for the forward, AP directional motion. That's the assumption. That's the hypothesis. That's the expectation. And see how results will look like. The results showed that for the eyes open and eyes closed case, the distance for the forward, the step length has been what? Decreased a little bit. Okay, that does make sense because with eyes closed, people tend to have a shorter step and no statistical significance though, it looks like. And for the lateral step width, there are increased step lengths observed for the subjects. Okay, so here we should think about what are the benefits of increasing the step length for the sensory perturbed situation. So if you examine the stability measure like eigenvalues for the Jacobian, in the lateral direction, it's initially unstable. And then if you increase the step width, those eigenvalues getting smaller and turns out to be stable region for the large, wide enough step width. So you can say that, okay, due to the sensor noise, system tends to behave like enhance the stability by increasing the step width. Not only the step length measure, we can also examine the variability, but the variability means for the average step foot placement point is here, suppose, but over 100 step, your step will be distributed with respect to the average value. and how variable is the measure for the variance. So step variability for the fore-aft direction, like a sagittal plane direction with eyes closed, increased, of course, because there is missing sensory information. For the lateral direction, the variability increase was a huge compared to, of course, the sagittal plane. For the after directional variability also increased, but the medial lateral increased a huge amount. So maybe this results show us that the lateral variability, great increase for the lateral variability might imply that it's really highly sensitive to the sensor noise, meaning your lateral foot displacement will use those sensory information, sensory feedback for control, the foot placement. So our hypothesis for having sensory feedback change, there should be a greater change for the lateral, implying that sensory feedback involved for the lateral foot placement has been supported. Okay, this is a quick summary for the sensory feedback analysis for the apply for the walking. So that wraps up the sensory feedback session. So we gone through the brief review for the feedback control and studied about how those sensory feedback framework can be applied for studying human posture control and even optimal control framework as well, and also simple example for the walking. And here are the list of suggested readings regarding to this chapter. Okay, with that actually conclude the whole course for ME585, the dynamics and control of human movement. We've studied the basics of dynamics and used those dynamic skills to analyze the repeated locomotion, walking and running. And for the control, we studied how the muscle model could be implemented for the walking control, the jumping and throwing control, and how sensory feedback could be used to analyze the posture control. I know this is a very, very fundamental and basic content to understand the human movement in terms of dynamics and control point of view, but I hope that this pretty basic knowledge could be served as a fundamental startup point or motivation or initial seed force for you to study more further extensive aspect of more complicated human body movement. And also, I really thank you for your attention throughout this semester, and good luck for your research. Thank you very much.